formalism in the setting of products of random matrices. To begin with, I'm just going to discuss some general results in subadditive and superadditive thermodynamic formalism. So we let sigma T be a subshift of finite type on alphabet 1 to n with primitive adjacency matrix T. And so this just implies that the subshift of finite type is topologically mixing. And we endow sigma T with the standard metric. We say a sequence of potentials phi is subadditive if each phi is continuous, and this inequality holds. And given a subadditive sequence of potentials phi, we can define the topological pressure by this limit. And the limit can be shown to exist by subadditivity and may equal -infinity. And for shift invariant mu, we can define phi star mu to be this limit, which again can be shown to exist by subadditivity. A theorem of Lau, Fong, and Huang, which was proved much more generally, says if you've got a subadditive sequence of potentials on sigma T, then the following variational principle holds. So as I said, they prove this a lot more generally. They consider a continuous dynamical system on compact spaces, and this result holds very generally. We also say a sequence of potentials phi is superadditive if minus phi n is subadditive. So that is, we instead require the other inequality. So before we had less than or equals to here, now we have greater than or equals to. And we can define the topological pressure by this limit. So note that we now have infimum here, whereas before we had supremum. But again, so this limit can be shown to exist by a superadditivity argument and may equal infinity. And for shift invariant measure mu, we can define as before phi star mu, where this limit now exists by superadditivity. So a theorem I prove in my paper is, so if you've got a superadditive sequence of potentials on sigma T, then again, the variational principle holds. And I prove this using a result of Cao, Pesson, and Zhao, which says that this holds. So here, the topological pressure is the classical topological pressure for additive sequences. And so like the result of Cao, Fong, and Huang, this also holds very generally, so for continuous dynamical systems on compact spaces. However, for my result, I have to use the specification property of the subshift of finite type. So it doesn't appear that my proof generalizes into the much more general setting. So we've got variational principles. There's an actual question of when do equilibrium states exist. And it turns out in the subadditive case, equilibrium states always exist. And this is because the entropy map and phi star mu are both upper semi-continuous in the weak star topology. However, in the superadditive setting, phi star mu is instead lower semi-continuous in the weak star topology, which means that the question of whether or not equilibrium states exist is a lot more subtle. Another natural question is, so if equilibrium states do exist, then do they have nice properties? So a nice property is the Gibbs type property. So given a subadditive or superadditive sequence of potentials phi, we say a shift invariant measure mu is a Gibbs type measure for phi if there exists C1, C2, such as all n, and for all x in the shift space, this inequality holds. So know that for additive sequences, so if you have equality here, then phi n will be a Birkhoff sum, and this definition will coincide with the classical definition of Gibbs measures defined by Bowen. So the main context in which subadditive and superadditive thermodynamic formalism has been studied is in the setting of products of random matrices. So given a finite set of GLDR matrices, for x in the shift space, we define A and X to be this matrix product. And for a word I of length n, we denote AI to be the matrix product A and X, where X is any point in the cylinder given by I. And for real T, we define the sequence of potentials phi T by this. So know that phi t is subadditive when t is positive and superadditive when t is negative.
Sir, sorry, sir. Just
Sure.
so what is c suffix n scripts for I belongs to that cn.
Say that again, sorry.
What is the cn? Actually, I missed that.
I can't quite hear. Are you able to type the question in the chat?
Is it just about the definition of CN?
Yeah, yes.
So what, it's a cylinder, right, Tom?
Oh yeah, sorry. CN is a cylinder, or so a word of length n on the shift space. Yeah, sorry about that. Okay. And we define the pressure function by the topological pressure of phi t, which is equal to this limit. So yeah, here Cn is the words of length n. And by the previously mentioned variation principles, this is equal to this, where lambda mu is the topological exponent of mu. And note that if a given time measure does exist for phi t, then it will satisfy that there exists C1, C2, such as for all n, and for all words I of length n, this inequality holds. The pressure function has been studied in several areas of maths. It's got important applications in random walks and also to wavelet analysis. In fractal geometry, it's been used to calculate the Hausdorff dimension of self-defined sets and self-defined measures. So the case where t is negative, which my results concern, has applications towards regularity of the first above measure, also to rigorously approximating Lyapunov exponents and to multifractal analysis. So I'm going to focus on the application towards multifractal analysis. So suppose that the matrices AI are strongly irreducible. So this means that they don't simultaneously fix a finite collection of proper subspaces. And we also assume sigma is the full shift, since the definition of strongly irreducible doesn't quite make sense in the subshift of finite type setting, although there are generalizations. And for real alpha, we let X alpha be this set, where lambda X is the Lyapunov exponent of the cocycle at X. So note that this limit doesn't necessarily exist, but alpha is the set of X such that lambda X exists and is equal to alpha. And we denote alpha min to be the minimum alpha such that X alpha is non-empty, and alpha max to be the maximum alpha such that X alpha is non-empty. And it follows from a result of Wong that for all alpha between alpha min and alpha max, the Hausdorff dimension of X alpha is given by this. So here the constant 1 over log m is just coming from the metric. The important bit is the Legendre transform of the pressure. This second bit. And another question is, so when is alpha to the Hausdorff dimension of X alpha analytic? And when this holds, it's called multifractal miracle, as it's kind of surprising that this can happen sometimes. The sets X alpha are typically very irregular. They're, for example, fractal sets. So it's somewhat surprising that it sometimes happens that the Hausdorff dimension of X alpha can depend so nicely on alpha. So the multifractal miracle is known to hold in certain settings, for example, when the matrices are positive or dominated. However, under more general conditions on the matrices, such as strong irreducibility and proximality, whether or not the multifractal miracle holds appears to be a very difficult question. So I'll now discuss some specific results that had been proved for the pressure. So Feng and Lau proved that if the matrices are positive, then for all real T, there exists a Gibbs type measure mu T for the pressure, which is more of the unique equilibrium state. And furthermore, the pressure function is differentiable and has derivative given by the Lyapunov exponent of the measures mu t. This result has been generalized to the dominated planar setting in papers by Brani and Rams, and also in a paper by Brani, Kainmaki, and Morris. In each of these cases, the Gibbs-type measure of mu t is in fact a Gibbs measure for a Holder continuous potential, and it then follows from classical results that the pressure function is in fact analytic on all of R. So in particular, the multifractal miracle holds. Previous results were known under more general conditions on the matrices, but only when T is positive. So one of these results is by Fong and Kainmaki. Says, so when the matrices are strongly irreducible, and again, sigma is the full shift, then for all positive T, there exists a Gibbs-type measure mu T for the pressure function, which is more over the unique equilibrium state. And furthermore, the pressure function is differentiable on positive T and has derivative given by the Lyapunov exponent of the measures mu T. It follows from work of Lepage and Guivarch that if the matrices are also proximal, so this means that there exists a matrix in the semigroup whose top eigenvalue in magnitude is simple and distinct. So if the matrices also satisfy proximality, then the pressure function is in fact analytic. And this is proved using transfer operator techniques and Swedrug properties of those transfer operators. So my results, I consider a general condition on the matrices and show that Gibbs-type measures exist for some negative T, and also that the pressure function is analytic in a neighborhood of zero. In particular, I consider the one typical one-step setting. One typicality was defined by Bonatti and Viana. You can think of it as being a generalization of the strongly irreducible proximal setting to subshifts of finite type, but speaking very roughly here. In fact, includes the strongly irreducible proximal full shift GL to R setting. And the methods should also work in the strongly irreducible proximal full shift GLDR setting. The reason I consider the one typical setting is because I use results of Parker and Prano, who consider this setting. So my first main theorem says, so if you've got a subshift finite type with primitive adjacency matrix T, and also if your matrices satisfy one typicality, then for all T less than zero, sufficiently close to zero, there exists an ergodic Gibbs-type measure mu T for phi T, which is more over the unique equilibrium state for phi T. And in the above setting, I also show that the pressure function is analytic in the neighborhood of zero and has derivative given by the Lyapunov exponent of the measures mu T. Perhaps surprisingly, these results cannot be extended to all of R. And this follows from work of Diaz, Gelfert, and Rams. They've got a few papers on this topic. And in these papers, they consider a subset of SL2R cocycles, which they call elliptic cocycles with some hyperbolicity. But the definition is quite complicated, so I'm not going to give the exact definition, but I'll discuss a specific example which is included in their setting. So if lambda is strictly bigger than 1, and so assume lambda is bigger than 1 and theta is irrational, and consider these two matrices. We also let sigma be the full shift on alphabet 1, 2, and we define phi t as before. We defined X alpha to be these level sets and alpha max to be this. So note in this case, alpha min is equal to 0, and this follows since the matrices are SL to R matrices and A2 is an irrational rotation. And so a theorem of Diaz, Gelfert, and Rams, which they prove over 2 papers. In the first paper, they consider the case where alpha is strictly positive. And in the second paper, they consider the more subtle case where alpha is equal to 0. But they show that the Hausdorff dimension of X alpha is given by, so 1 over log 2 times by this quantity. And they moreover show so the map alpha to the Hausdorff dimension of X alpha is concave on 0 to alpha max, and the right derivative at 0 is equal to some positive and finite to C. And it's a straightforward application of this theorem that for all t less than or equal to minus C, the topological pressure is equal to this quantity. This is kind of a restricted variational principle over the measures such that the Lyapunov exponent is equal to 0. And also, for t strictly bigger than minus C, the topological pressure is strictly bigger than this quantity. So in particular, the pressure function is not analytic. It is, however, still unknown whether the pressure function can fail to be differentiable. So their results imply the pressure function is not analytic, but not necessarily that is not differentiable. To show that the multi-fractal miracle holds in this setting would require showing that the pressure function is analytic on t bigger than minus C and differentiable at t equals minus C. But again, this appears to be a very difficult problem from what I can tell. So I'll now discuss the main ideas that I use in my proof. So for simplicity, I'll just consider the case where sigma is the full shift and d is equal to 2. And for real t, we define the transfer operators LT, adding the space of continuous functions on the product of the shift space and projective space by this. So here, AI star is just the transpose of the matrix AI. So IX is the element in sigma given by appending I onto the beginning of X. And I use overline to denote points on the projective space. And Park and Pereno showed that there's a spectral gap for this family of transfer operators for all t in the neighborhood of 0, and that the spectral radius behaves analytically. So this family of transfer operators is based on the ones originally defined by Lepage. But the transfer operators which defined by Lepage only act on the space of functions on the projective space. And when t is strictly positive, you can show essentially everything that you hope to be able to show only by considering the transfer operators to be acting on functions on the projective space. However, it turns out it's important in my proof that the transfer operators are defined to be acting on functions on the product of the shift space and projective space. I'll explain why in a moment. Using the eigendata from the spectral gap, we can define measures nu t on the product of the shift space and projective space. And we can project these measures onto the shift space and to define a measure mu t. And also we can project this measure onto the projective space to define a measure eta t. And so the measures mu t are the ones that come up in my theorem. So these are the measures that I will show you have the Gibbs type property. And it turns out that the measures eta t are kind of the analog of Furstenberg measure corresponding to the measures mu t. So you can define Furstenberg measure in terms of Osler-Detz subspaces. And we can show that the measures mu t are ergodic. So in particular, Osler-Detz theorem holds. So then, eta t turns out to be the analog of Furstenberg measure for the measures mu t. But this isn't something you get for free, and you have to prove this. And so this is proved by. So to prove this, I first prove large deviation principles for the measures nu t, using analyticity of the spectral radius and also analyticity of the transfer operators in some appropriate sense. The large deviation principles that I can prove for the measures nu t coming from the analyticity of the spectral radius is what allows me to show that the measures eta t, so the analog of Furstenberg measure for the measures mu t. So this is a key step in the proof, and it's this step that doesn't appear to work if you only define the transfer operators to be acting on functions on the projective space. When t is strictly positive, to show that mu t is a Gibbs type measure requires showing that So E to T is not supported on the projective subspace. So this has been used in papers by Lepage and Guivarch, and also in a paper by Pereno. However, in contrast, when T is strictly negative, we instead require showing that E to T has a certain Rossmann property. So for a measure on the projective space, we define its Rossmann dimension as you'd expect it to be defined. And we can show that the measure μt has the Gibbs type property by showing that the Rossmann dimension of E to T is strictly bigger than minus T. So know that in the positive T case, to show that E to T is not supported on a projective subspace isn't a too difficult condition to show. However, the condition that the Rossmann dimension of E to T being bigger than minus T is a lot more subtle and involved to show. Also note that the Rossmann dimension of E to T being strictly bigger than 0 implies that E to T is not supported on a projective subspace. So the condition coming for negative T is strictly stronger than that comes up for positive T. For the first measure of a Bernoulli measure, so i.e. in the strongly irreducible proximal setting, it was previously known that the Rossmann dimension of eta is strictly bigger than 0. And this is proved essentially only using large deviation principles. So they're large deviation principles proved using transfer operator techniques and special gap properties. And we can adapt their argument using the large deviation principle proved for the measures μt that I've already mentioned, which is proved using analyticity of the spectral radius. Large deviation principles that have been proved for the Bernoulli measure μ0. And the estimates that there exists CT and RT strictly positive, such that RT tends to 1 as T goes to 0. And for all n and for all words I of length n, this inequality holds. So you can combine this inequality with the large deviation principles that have been proved for the Bernoulli measure μ0, and combining this with the large deviation principle proved for the measure μt, you can adapt the argument in the Bernoulli measure case to show that this condition holds for all t in a neighbourhood of 0. So that's all I plan to say. I'm not sure how much time I have left.
Thanks very much.